University of Tennessee.
Great, thanks. Thanks to the organizers for having me here, although providing some of the budget from the department, man, I guess they had to invite me. So it's still a pleasure to be here. So I'm going to tell you about some work that involves Bayesian searches, basically to find a quantum phase transition, a particularly challenging one, transition between a superfluid and insulator in the Bose-Hubbard model. This is work done under the auspices of our MRSEC, the Center for Advanced Materials and Manufacturing, and supported by that as well as the AI Tennessee initiative, and work done by lots of different people. Great postdoc, Matthias Stam, my student Harini, who's currently looking for a postdoc and can bosonize anything. So if you need something bosonized, you should definitely hire her. Arben Biswas, who works with the UT Oak Ridge Innovation Institute, and Baron Rosenau, a long time collaborator of mine in Leipzig. All the slides will be on my website, and we have this GitHub Del Maestro group repository and all the codes to generate every plot in here. You can download off there and run for yourself along the lines of what we just heard about reproducibility. Okay, so this is the goal. What we want to do is just find the critical coupling in the 1D Bose-Hubbard model. So this should be an easy thing, right? This is really toy quantum matter. It's software bosons. Let's focus on unit filling, the easiest case. There's no exact solution. This is an interesting case where there's a paper by Haldane where there was thought to be an exact solution in this model, but it turns out that you can't just put lead linear gas on a lattice because of the software nature. So there is no exact solution, but feels like there should be. It's a pretty simple problem. The phase transition is known to be in the BKT universality class. So this is sort of problematic for the following reason, that we know that such transitions have extremely slow logarithmic scaling, finite size scaling at the transition, and nearly logarithmic scaling close to criticality. So this is a case where, doing the thing that we normally do as computational physicists of just doing finite size simulations and trying to scale up to the thermodynamic limit is very hard. And here, this is a case where the RG is going to be extremely important to figure out what's the right finite size scaling to do. And that's where this Bayesian approach is going to come in. And the thing that kind of motivated us, although full disclosure, I mean, when we set out to do this project, the goal was not to pinpoint this transition, but we ended up having to do that to answer some other questions. But one thing, if you look in the literature over the last 25 years, you can find any value for this coupling constant that you want within, 200%. And papers that come out year to year are 6 epsilon or 6 sigma away from each other. So there's no way that this is just uncertainty in approaches. Either everyone's wrong or everyone's right, and there's some problems with how things are going on. So we hope that we've closed this particular issue, and I'll tell you about that. And this is work that's, I would say, 98% done. The paper is currently almost written, and there's just a few things. Okay, so just to get everybody on the same page, so the model, basically the starting point, and we're going to, one of the themes is there's going to be two kind of parallel approaches to understanding the system, but just thinking about it in second quantization, I just have 1D interacting software bosons, and imagine some periodic potential. So I have this external potential here, it could be a cosine or something like that, and then there's some interactions that are basically soft core. So I can have two bosons on the same site. And so in the limit where I have some, let's say, reasonably strong periodic potential, because of the software nature, I could get multiple occupancy on a given site. And so the conventional approach, how we would derive such a lattice representation starting from this Hamiltonian, is I just imagine some localized, something like Bernier functions, some localized wave functions, and I can write these field operators in terms of some local lattice operators, projecting the lowest band, and I just get the single band Bose-Hubbard model that hopefully people are familiar with some hopping J that crucially depends on this free Hamiltonian here. It depends on details of this external potential, and I have some interactions that depend obviously on this soft core microscopic potential here. And this is a Hamiltonian that is very suitable for simulations, be it quantum Monte Carlo or DMOG, provided that you can cut off the local open space. And so this is where the computational physics aspects of this talk will lie. But the way that we're going to identify the transition, so okay, this tells us I need to measure something, right, from this Hamiltonian, and then ask, well, is it one, is there an order parameter, let's say superfluid density, is it 0, is it not, right? So I want some kind of more grounded way to identify the location of the transition. And I can do that by thinking about this potential being weak. doing some conventional bosonization. And under such a procedure, the result is something that looks like a Sine-Gordon Hamiltonian. So this is the liquid Hamiltonian, where it has only a single parameter here, K, which depends on the interactions, the details inside here. The hopping J depends on the details of this periodic potential. And the existence of this cosine term, this pinning term, which basically pins the density. This is the thing that is responsible for the presence of the insulator, even in 1D here, is one can think of it in terms of, at least at unit filling, in terms of the clock processes. And so the kind of approach that we're going to take is to compute things for this Sine-Gordon Hamiltonian, or even better, this liquid Hamiltonian, and then try to match those with numerical simulations in a very consistent way. All right, so we know a lot about the Bose-Hubbard model. It's such a great, the original Bose-Hubbard paper here, this one with such a readable and wonderful paper. I encourage you to read it if you haven't done it recently. It's really nice. But we know we have these mod lobes, so as a function of filling in this direction and the strength of the hopping, so think about that as lowering this periodic potential. We have these mod lobes, which are insulating at unit filling. And at fixed filling, let's say we fix at expectation value of n equal to 1, I can basically cruise along some trajectory, and I can go from an insulator to a superfluid. And in this talk, you'll see me switch back and forth between J over U and U over J, and that's just a function of the method might make it easier to think in terms of one or the other. Okay, so this is the phase diagram in 1D. And I want to identify this critical point here. I mentioned this before. The original idea of generalizing Lee-Linegar didn't work because of these hierarchizations. And so we don't know. We have no exact known value for what this is. We need to figure out how to do it in some way. So there's been lots, and I highlight lots of numerical work on this over many, many years. These are just some that I picked up from the early 90s. There's quantum Monte Carlo, there's DMRG, there's exact diagonalization, there's analytics, there's perturbation theory, you name it, it's in here. These are the values that are reported in these papers with their error bars. There's maybe some kind of convergence going forward, with the most recent kind of best guess being from 2012. I'll return to this paper later, but look at the error bar on this thing, right? So this error bar is so small on this value. That's how sure they are that this is the right value of the critical coupling. If I just take the next best one, this is like 8 sigma right here. So there's no kind of statistical way that the error bars can be so precise that there must be some systematics or something that we're not fully understanding here. And again, I'm not kind of saying that what anyone did here is wrong. I'm just saying that there's some maybe unifying thing that we need to think about. All right, so how do we know how to pinpoint this transition? Well, I told you that this Sine-Gordon Hamiltonian, or the Bose-Hubbard model, has this BKT transition. So it's unbinding of vortices in this Bose-Hubbard model. You should think about that like instantons. So we know that there's some RG equations that you can solve. You can solve these in a brute force way. And the RG flow looks like this. So let me just walk you through it if you're not super familiar. So on the x-axis here is the Luttinger parameter. And the interactions in the Bose-Hubbard model get weaker as I move to the right. So over here is kind of non-interacting bosons on this side. And so this transition, so there's these flow lines described by this. And so essentially, if I have weak enough interactions, what this is telling me is that K flows to some finite value, which corresponds to weak interactions. But V, the importance of this pinning essentially always goes away. So this is the superfluid side, right? V flows to 0. If I have weak enough interactions, the presence of some periodic potential is not enough to localize these bosons, and I have a superfluid state. Beyond some separatrix, some critical value K going to 2, I know that again from this Sine-Gordon Hamiltonian. On the other side, there's some mod insulating state. This thing is not a Luttinger liquid. The bosons become localized. Right, my phi has some finite expectation value, which pins this thing. V flows to infinity. That's the strength of the lattice potential, and K essentially flows to 0. Although that's maybe not a very meaningful statement in the sense that it's not really a Luttinger liquid on that side. So this quantum Luttinger liquid is stable for any K greater than 2. And so again, this is a property kind of 1D and interference effects related to the existence of this pinning potential, that if I start to increase interactions and go this way, then I actually can have a continuous second order quantum phase transition basically in this the value class here. Okay. So what you should take away from this is that the 1D Bose-Hubbard model is BKT. I know that the transition occurs at k equals 2 in that Stein-Gordner, that Lenzner liquid picture. And so I'm going to fix myself at unit filling. And so if I do that, so I can take this Hamiltonian, I can do this Bosonization I discussed. And so the goal will be I want to compute observables with QMC or DMRG or something from this Bose-Hubbard model. This thing, this Lenzner liquid Hamiltonian is quadratic. I can compute anything that I want, but I'm willing to kind of turn the crank enough, higher order correlation functions, whatever it might be. And so if I can extract K as a function of U over J in this model, well, then all I need to do is invert that function and figure out when K is equal to 2, what's U over J. So that's the approach. So this is the critical point here. And crucially, I need to do this as L goes to infinity. So I want some easy to measure quantity in the Bose-Hubbard picture, so some diagonal estimator. And I want it as a function of U over J. If I can do that, I can do this inversion and find the critical point. And that's essentially what the vast majority of those data points that I showed you have done in some way or another. They've chosen different K-dependent quantities, correlation functions, gap, superfluid density, fluctuations, you name it. I'm going to focus on, I think, the most useful one here. And that's bipartite fluctuation. So here I'm showing this at half filling, just so you can see. But this is a very simple diagonal estimator in the Bose-Hubbard model. I just ask, what is the expectation value of the number of particles fluctuating between two regions of the system? And I make that, I define some region of curly L sites here. So in the Bose-Hubbard model, this is a fully diagonal estimator. All I have to do is count the number of sites in a given state. In the Lenzner liquid picture, it's also pretty easy. I have this density operator, I bosonize and integrate, and I just get the values of this phi field at the ends of my region. And it turns out that you can calculate, well, from this, you can probably see that you can calculate an expression for this exactly. It looks like this within the Lenzner liquid. So it has a prefactor here, which is the thing I want K. So if I can measure this in Bose-Hubbard, then I can then compare with this or fit to this functional form. And another very nice thing is, okay, there's some microscopic details here, but in the limit where these microscopics, this UV shouldn't matter, this thing is just the F, the thing I can easily measure from Bose-Hubbard by just measuring, is linearly proportional to K. So I just need to fit a line, basically. If I plot this in the right units, this thing is a chord length. So how, that's the best case scenario. It's non-linear regression. I just need to pick out this line. And that's what Stefan Rachel and Karen Leher did in this kind of current state of the art from over 10 years ago now. But there's this subtlety about RG and finite size effects here. So here's this flow diagram I showed you before that I got from just brute force solving those RG equations. But you can analytically solve this thing in a way that kind of beautifully represents what it means to have RG flow and finite size scaling. So if you reparameterize in terms of this new parameter zeta, you can rewrite this RG flow in terms of these two coupled equations. The first is an integral equation that says, if I think about two different system sizes, so I imagine that system size flows me in this direction, so the thermodynamic limit is down here, right? So if I can measure two values of the Lenzner parameter K, then I can solve this equation for zeta, knowing what zeta is, then uniquely determines the flow line. So I do two simulations at the same value of U over J for my Bose-Hubbard model. That gives me two different predictions for K. Then I stick those in here, I solve this thing, that gives me zeta, that gives me a flow line. So this is just this finite size scaling procedure, and here's my RG scale as usual. And so what this tells me is that in the superfluid phase, this zeta is greater than 1. K goes to 2 being the location of the critical point. And that's everywhere where this V potential, the pinning is irrelevant. And then right at the superfluid mod insulator transition, this thing picks up a value of 1. And in the mod insulating phase, it's less than 1. And this is where K goes to 0 and the V goes to infinity. But this is extremely challenging from a numerical standpoint to do finite size scaling on a given set of simulation data, because if you actually, you can solve these things analytically close to this separatrix, the critical separatrix here. And what you find is that even in, deeply in the critical regime, the superfluid finite size scaling has this type of form, 1 over L to some power. Again, a very, very weak power, right? K star is basically 2 here. So this is some extremely weak power. Along the separatrix, right at the transition, you have this logarithmic scaling, and you also have this near logarithmic scaling on the mod insulating side, where eta is very close to 1. So depending on where you are in this phase diagram, the functional form that you need to do for your finite size scaling is different. So this is kind of giving some hint of what might be going wrong when people were finite size scaling numerical data. Doing the kind of usual empirical thing that we do, which is do simulations at different L's and then try to extrapolate as 1 over L or maybe 1 over log L or L to some power, right? The actual values of U over J that you simulate at will have different functional forms. So it's really hard. And we can see that by carefully reanalyzing this paper from 10 years ago or so, where they predicted this J over U with some very small error bar. So they actually have this K as a function of J over U. So they use very, very large at the time, pretty amazing open boundary conditions, DMRG, where they have to truncate the bosonic Hilbert space at some number of bosons per site. And they compute these fluctuations and then fit to this expression right here. So this is the result. So they use a left-sided region in this open boundary conditions. I'll come back to that in a second. This is the data. We've reproduced data in their paper as a function, the fluctuations as a function of this chord length. Out in this region, if you take the log of it, it should be completely linear. When they do fits, this is a reproduced figure that is also in the supplementary material of that paper, where they predict K being close to 2. What they find is basically where they choose to do the fit along this region gives, and the width, the number of points in the fit, basically gives quite different values for K. And so if one looks at that, you get very large error bars. These are the 3 data points that they show in this paper, and they extrapolate within some error bars and get this value of K. So, you know, this is, again, just a reproduction of what's in this PRL from a number of years ago. But so these are the 3 system sizes that they measured at, 128, 256, and 512. We were trying to figure out what might be going wrong with this fit. So we redid this at many more system sizes, and this is the data. So they chose these 3 points, which one can reproduce exactly. But if you actually fill in the data here, you see this highly strange function of L. And clearly, clearly there's a big problem. Oh, I keep going the wrong way. All right. There we go. Clearly there's a big problem here, right? So they chose these 3 and drew a line through them. But if you really understood the details of this function, which is quite complicated based on where you are in the phase diagram, you'd predict actually the completely different phase. So here you'd say superfluid, but if you chose, you know, these points instead of these ones, you'd predict mod insulating phase. So this is not the right way to do these fits. And so a natural thing might be to say, so this was our idea 1, let's just carefully redo the analysis for open boundary conditions. So they were effectively using a periodic boundary conditions Lunger liquid prediction for an open boundary condition simulation. Now, we're always taught, well, if the system's big enough, you don't have to worry about it. Periodic, open, doesn't matter. But boundary effects can actually be quite important. That's why there's things like boundary critical phenomena. So if you redo this analysis for OBC, where the region starts at some location X, you get a different function. And in this same limit that I talked about before, you actually get a prefactor that doesn't even agree with the PBC result. So you're highly influenced by the boundary in this case. And so a simple fix, which, you know, I said to Matthias, I said, well, obviously the simple fix is just use a centered region and big system sizes. And that does work considerably better if you do that, if you use a centered region and all this, but it still actually highly depends on where you do the fit. So in the region out here where the Lunger liquid model should be most effective at describing fluctuations, you see that there's strong deviation. So each of these is for a different value of U over J or J over U. So you see there's these strong deviations. So it's not really working. Even worse, even if you do this properly, what you can find is scaling that violates the RG. So for some regions in the superfluid phase, you can actually see that these lines are either flat or even increase as we increase the system size. And that's completely in violation with RG. So this is something needs to change here, basically. Open boundary conditions is hard because of these boundaries. And so there's a ... here because poor Matthias and Harini and others, I said, well, it's because we're not properly taking into account higher order terms, or you need to worry about Friedel oscillations, or you need to do this and that. We tried many things to do this with open boundary conditions, and essentially nothing worked without some, extremely careful rescaling of the data. But finally, we realized that maybe everybody in the room knew this. I should have been more careful. You really, obviously, if finite size scaling is coming from the RG, then you better use the right boundary conditions, the ones consistent with the given RG formulation. And what's known, these are simulations, old simulations of the classical XY model, that if you have OBC, you can have image as in 5, where it redoes the conventional KTRG with open boundary conditions. And you see, so here's the solid lines are what I showed you before, and you get these huge deviations from the RG flow near the effects of the boundaries. And that's because effectively the underlying model is different. It's a non-local sign-Gordon Hamiltonian. So you have to work extremely hard if you want to do finite size scaling with open boundary conditions in this case. Okay, so then the easy thing is we'll just do PBC. That's the easy thing, right? You should just do periodic. Yeah.
Yeah. Question. So this sensitivity to boundary condition.
Yeah.
Is it important at the transition, near the transition, or is it also important in the superfluid phase?
Yeah. So it can even become important in the superfluid phase, and that's essentially depends where you are, and that's related to the position, the presence of these image vortices. Yeah. So it affects you everywhere in the phase diagram, and that's basically because of this non-local piece right here. That's a great question. So, the short answer is just do PBC, periodic boundary conditions. So one can do that in iTensor or your favorite DMRG. We have our own ground state QMC code called Pigsfly. But the problem is, if you do, as everybody knows, why don't you do periodic boundary conditions in DMRG? Well, if you want some given accuracy and you keep M states, you need M squared states. So it's super hard. This is also a case that due to a Goldstone mode, any projective QMC, like we heard about earlier, actually has an extra factor of L scaling in it because I need to project out. And instead of it being exponentially decaying, it's only a power law. And so these turn out to be very challenging. In fact, single L evaluation of K, I do one simulation, takes about 10,000 CPU hours for periodic boundary conditions in DMRG, and it's much worse for QMC, 100,000, because you need extremely small error bars to be able to resolve this. So these are very expensive function evaluations, but we did it for 2 different values of U over J, that's shown here. And now these are much smaller system sizes, but now you can see it works much better. So with periodic boundary conditions, this fluctuations as a function of the chord length are a straight line, and it basically doesn't matter where we fit this straight line. We get a consistent value of K. We can then do that same plot before K as a function of 1 over log L. This is the data right here. Obviously, it goes to larger values of 1 over log L because we're limited by system size. But these dashed lines are actually the RG predictions. So these are fully consistent now with RG. There's no, just scaling with 1 over log L, we can actually use the right functional forms. And if you flash up the OBC on here, it's just totally wrong. Now, one should take these error bars on the OBC as being more kind of uncertainty intervals insofar as you change the location of where you do the fit in OBC. And if you go to really small systems in the center where the boundary doesn't matter as much, you can move these up and down. But a naive kind of OBC situation here is not going to work. Okay, so now all we have to do is, well, we just do a bunch of simulations with PBC and then find this K equals 2, where the transition is. But that's, can we do better than a brute force search? And this is where the Bayesian methods come in, which I didn't really know about before. And I'm always doing grid searches, 1D, 2D, higher dimensional grid searches, which basically are not the best thing to do if you have expensive function evaluations. So here's the problem. What do we want to do? We want to identify K of U of J when K is 2. We don't know how to invert this function. We only know it numerically. So we have to perform at least 2 costly simulations for each U over J. That's because we need to flow down one of those RG lines. So we have to do 20,000 CPU hours minimum per U over J. We know the transition occurs at zeta equals 1. So here's some computer budget where each of these is, so the zeta equals 1 is the transition. So we just plot this as 1 minus zeta squared, such that the transition should occur when this thing's exactly 0. Here's 1, 2, 3, 4, 5, 6, 7. So, on the order of 100,000 CPU hours or so. So this is a case where we only know the zeta at fixed values. Function evaluations are extremely costly, right? And we can't perform gradients because we don't know what the functional form is. So basically at this point, we can recognize that minimizing this thing is just an optimization problem. And it's a non-parametric optimization problem because we don't have a model, right? So we need to do some kind of non-parametric regression, and that's a Gaussian process. So what we'd like to do is figure out what that curve is so that I can identify the value of U where its minimum is, but I don't have just some fitting function. Sure, I could use some higher order polynomial or something like that, but I want to have a parameter-free model, right? So that's just a Gaussian process. And then the structured piece of the Gaussian process comes in by putting all the physics knowledge that we have about what might be happening locally. So that's an SGP, it's just nonlinear regression without parameters. So this y of x here is the function we want to learn, right? We want a probabilistic model of this function. This is our distribution. The t's are just the targets. This is the evaluations that we have that are costly at these simulation parameters u over j. And these are constructed from the usual prior distributions. So we use some Gaussian error model for the noise. I mean, if you're interested, I'd be happy to talk more about this. I'm just wrapping up. Some particular type of kernel in this Gaussian process, and we can constrain it in different ways. And so this